Let's talk about composite functions. Composite functions, or when you put one function inside of another function, we write them by using this little open circle, which means of. Another way of saying this is f of g of x. That's how we would say that in words. And it looks like multiplication, but it's not multiplication. That signifies a composite function. And this is the other way of writing it. So that's like whatever is closest to the x. In this case, g. That means we're plugging g of x into f of x. So let me show you what that looks like. If instead of finding g of f of x, we're finding g of f of 3. So in this case, our inside function is f. So you start with the inside. We're going to find what is f of 3. So our two functions are defined here. To find f of 3, we would plug in 3 into the f function. 6 minus 7 is -1. So f of 3 is -1. So because f of 3 is -1, I'm going to substitute f of 3 with -1. So now we're going to plug -1 into the g function. So I get -1 squared plus 4 is 5. So in total, g of f of 3 is 5. We found f of 3 is -1 and g of -1 is 5. Let's look at what that looks like when we're actually talking about functions and not just plugging in a number. So when we're talking about functions, again, we're looking at the inside function first. So g of x is on the inside. So that means we're going to plug g into f. F is my outside function. So we're going to take g and we're going to plug that in everywhere there's an x in function f. So in this case, what that would look like is 4x plus 1 is where that x is, but then there's still a -3 in the numerator and a 2 in the denominator. And then we just work through simplifying this. 4x plus 1 minus 3 is 4x minus 2 over 2. And then we can divide both of those by 2, 2x minus 1. So f of g of x equals 2x minus 1. Whenever you're looking for domain of composite functions, you're going to look at the domain of the inside function and then your final domain. So for our inside function, there's no even roots. There's no x in the denominator. Same with our outside or our final function. So our domain is all real numbers. So looking for even roots and looking for a quotient. We never want the denominator to be 0. So let's try that again. But this time we're going to plug in f into g. So we're going to take function f and plug it in everywhere there's an x in g. So in this case, we have 4 times, and then we're going to plug in f, x minus 3 over 2 plus 1. Well, when we multiply 4 times x minus 3 over 2, we get 2 times x minus 3 plus 1, or 2x minus 6 plus 1, or 2x minus 5. So when we plug f into g, we get 2x minus 5. We never had a quotient. We never had an x in the denominator. We never had an even root. So this time, again, our domain would be all real. Bless me. For all real numbers. So same function, but this time composite functions, what they can also look like is plugging one function into itself. So this time we're going to plug g into g. So I'm going to take g, and where there's an x, I'm going to plug in g. I'm plugging function g into function g where the x is. And then we're simplifying. We distribute, combine like terms. So g of x is 16x plus 5. We had no x's in the denominator. We had no even roots. So our domain is all real numbers. Same thing with f. We're going to plug f into f. So I'm going to take function f, and where the x is, I'm going to plug in f again. So it looks like this. And that looks pretty messy. What can we do to simplify this? What we could do is multiply both the top and the bottom, the numerator and the denominator, by 2. Because if I multiply both the numerator and the denominator by 2, I'm really just multiplying by 1. 2 over 2 is 1. So when I multiply the numerator by 2, I get x minus 3 minus 6. So here the 2's canceled, but then I also had to distribute it over here. And in the denominator, 2 times 2 is 4. So that would be x minus 9 over 4 is f of x. We do have a quotient here, but we never had an x in the denominator, and we had no even roots. So again, our domain is all real numbers. So same idea, 2 different functions. 4x to the negative first power, we can leave it like that, or you can rewrite that as 4 over x. I think it's a little bit easier to think of as 4 over x, so that's what I'm going to do. And the first thing we're going to do is we're going to plug in g into f. So I'm going to take g, plug it in to f. And again, it doesn't matter whether you use 4 over x or 4x to the negative first power. I'm just going to use the 4 over x. So when I plug g into 4 over x, instead of 4 over x, I have 4 over 5x minus 2. And that can't be simplified any further, so that's just f of g of x. Our domain is limited here, though, because we have an x in the denominator. And we know the denominator can never equal 0. So when I solve for x, I get that x cannot be 2/5. That's my domain. X can be any number except 2/5, because 2/5 would make the denominator 0. All right, next we're going to plug in g into f. No, sorry, we're going to plug in f into g. F is the inside function, so we're plugging f into g. And when I do that, I have 5 times 4 over x minus 2, or 20 over x minus 2. And you could probably leave your answer like that. I'm going to combine it into one thing by getting a common denominator. So 20 over x minus 2x over x. So now they have a common denominator, which means I can write it as 20 minus 2x all over x. So again, you could probably leave your answer like this, but this means the same thing and looks a little cleaner because it's all over x. Because we have an x in the denominator, our domain is limited. If we plugged in 0 for x, our denominator would be 0, so x cannot be 0 is our domain. Plugging g into g. So we're plugging 5x minus 2 into 5x minus 2. And then simplifying. That one's pretty easy. And there are no denominators where it could equal 0. There are no even roots. So our domain is all real numbers there. Plugging f into f looks a little messier. Because remember, f again is 4 over x. So in this case, maybe it would be easier to keep it as 4x to the negative first power. So I have 4 where the x is. I'm going to plug in 4x to the negative first. And then I'm going to distribute that negative first power. Let's use something other than yellow. So I have 4, and then this becomes 4 to the negative first, and then that x becomes x to the first power. So 4x to the first power over 4 to the first power, or just x. Our domain, we did have an x, or we didn't have x in the denominator. It doesn't look like we did, but we really did, because 4 over x, or 4x to the negative first means 4 over x. So that x is in the denominator, which means it cannot be 0, or the denominator would be 0, and the function would be undefined there. Few more examples where instead of finding the new function, the composite function, we're finding a composite value. So again, we work from the inside out. So we would start by finding f of 5. So I'm going to plug in 5 into f. 3 times 5 minus 8 is 7. So then I'm going to find g of 7. So when I plug in 7 for g, I get 49 times 2, or 98. Let me erase these, and we'll try another one. So next to it, we're going to start by plugging in 5 into g. So when I plug 5 into g, I have 2 times 5 squared, or 50. So now I'm going to find f of 50. So 3 times 50, or 150, minus 8 is 142. So f of g of 5 is 142. So always start on the inside and work your way out. So next one, we're going to start with g of 5, plugging in 5 for g. 2 times 5 squared is 50. So now I'm going to find g of 50, and g again is 2 times 50 squared, which would be 5,000. So g of 5 is 5,000. And then f of 5, start on the inside. F of 5, 3 times 5 minus 8 is 7. And then I'm going to find f of 7. And we have 3 times 7 minus 8, or 21 minus 8, 13. So f of 5 is 13.